My name is Eric Pershey. I work at Argonne National Laboratory. I work in the Leadership Computing Facility. We deal with supercomputers at Argonne. We're a production resource. Here's my outline. I'm just going to go through a few things. Who am I? How I get things done. Some of our ALCF machines. We have some quite large sets of data we deal with. I'm not going to call it big data, but we have lots of it. What's next, and questions and acknowledgments. So I'm Eric Pershey. I'm a software developer, as I said before. I've had about 10 years experience in Python. I've also had probably about the same amount of time in Django. I've done a lot with that. My boss would say I'm a fanatic tester, and I program very fast due to the way I test. I'm also a lightning photographer, a train spotter, and astronomer. I'm always learning new things. That's the nice thing about Python, and the environment keeps evolving. So I'm always learning new things. So please correct me if I'm wrong. As my wife says, Python is my first language, English is my second. And my goal is functional and design. So if we could just do all websites in monospace fonts, that would be fine with me. All right, so the Leadership Computing Facility was established in 2004. It's a home to a number of supercomputers. It's a DOE Insight resource. An Insight resource is it's a program by the Department of Energy to allow people in the industry to get access to our large machines. They have to go through the approval process, and we, I think, run about 12 Insight projects right now. These include people such as GE and Boeing and other things like that. In 2014, we supported 342 projects. There's also another program called ALCC, which only runs about 30% of the time of the machine, whereas Insight runs about 60% of the machine we have to devote to them. We have 1,400 users. We've delivered 5.8 billion core hours in compute time, and we've resulted in more than 150 publications. So our biggest machine right now is Mira. It's a 10 petaflop Blue Gene Q machine. It's number 5 in the top 500. My job when I first got there was to test the machine and basically destroy it until they could get everything fixed and then actually use it. We're getting another machine that was announced, I think, about a month ago. It's called Aurora, 180 petaflops. It's a Cray in 2018-19 time frame. And then our machine that we shut off and sent to be recycled was our machine Intrepid, which was a Blue Gene P, which was 0.5 petaflops. And we got that in 2009. All right, so one of the things I do well is get things done and do it as fast as I can and as efficiently and with maintainability in mind. So I'm just going to call this HDIGTD because, that's what government people do. We make acronyms. All right, so basically I design the system. This is actually quite quick sometimes. I use DIA. I use DIA to do this. I use other various things, whiteboarding and stuff like that. The one nice thing I can use about DIA is I have ways that I can build the entire database from DIA, and I can have it create the database for me, and then I have a diagram for the database. And I also can go in the reverse direction where I can have a database and I can make a DIA diagram of that database. So I have multiple ways I can do that. Another thing is I go down and I define each of the components of the system. A lot of the times people just say it's going to do this. Well, I say, well, that is a little piece here and here and here and here and here. And if you isolate each component, you can easily test them because you have known inputs and known outputs. So I build to test. And then I also think idempotent. I had a problem trying to figure out if this was the correct word for this. But what happens is when we run we have a lot of systems that run. We actually use Jenkins to run a lot of our ETLs for loading data in the data warehouse. Well, if you were to give them the same input, the same database would come out from that, no matter if the data was already existing in there. So it's not going to duplicate rows, and you're going to be able to keep rerunning these if you have problems and just keep going forward. And then quickly mock up a system. That's the goal. If you want to test something to see how it works, get it going, get it working. And then you might throw it away when you're done, because what you've done is you have the path towards to get to the final end goal. Now you know how to get there. Now you can go back and make it better. What you can do is you can try to rebuild this thing. So if it's a production-worthy thing, this is most likely what I'll do. Is most of the time I predict about 3 times, but before I get to the final version that will just stay in, that will stay in production and run for a very long time without error. So basically, you can dig into the design. I think Jonathan talked about this before, but you do a lot of profiling of code. One of the things I probably do is do some more Python stuff. But you check for long runtime code, the chunks of it. So you can use cprofile to do that, and some other various things such as run snake run. Look for memory problems. Some of the times when you're dealing with data warehouses, if you're loading all the dimensions into memory, well, that can get kind of big. And then when you correlate them, you can really have memory problems. Look deeply at questionable code. If you can't look at a piece of code and understand what it's doing, you probably need to rewrite it. And then look for points of failure. In Python, there can be a lot of points of failure. Just be careful what you do. Then you can integrate parts of the old code. I don't suggest, some code can move over, especially if it's done well and tested well. But you don't have to bring it all over, but some of it can. Maintainability, that's another thing I go for. When I write the code, I don't want to babysit the thing. I want to make a system, get it done, put it in Jenkins, run, and continue to the next one. Then testing. So basically, I'm a fanatic tester, but I do understand that there's levels at which you can test, and it does cost time. So certain things I'm working on a redesign of our accounting system. Part of the reason why we have to build our own accounting system is because it's not just a core hour. It's a core hour in where it was run on the machine. So it has another factor of where it is and how long it was. And then there's some other factors we need to incorporate. So that component, I extracted the business logic because that's one thing I keep separate, and I will go around and find all the business logic and isolate it, and then I'll be able to test it. So the piece of business logic that determined how things were charged had 128 branches. All of them were tested. And actually did not take as long as you would think to test that many branches. The only part that's not tested is the type safety of each of those. So I was going to put that on, but if I have control of the ins and outs, I may not do that. You can have a lower amount of testing. Don't cover every branch, but you cover some of the major functions where you're looping a lot, doing the same thing over. You just need, you have some case statements or if statements. You need to get some of those covered. And if you don't test your code, don't let me see it. Because I'll find something, and if I don't find anything, I will be impressed. A few different testing methods. A lot of times I use unit testing. So I use a lot of unit testing for in and out. What's it called? Nose test. I use nose test heavily. And then I have functional testing where I'll actually test, I'll have like a test runner that I'll actually run, and I'll actually run through the entire system and actually test the entire system. And then there's integration testing. I'll actually make sure it can actually talk to the system that it needs to talk to correctly and get the expected output, which is sometimes not the case. So a few of the LCF systems we built with Python, which were mainly a Python shop, we have the test harness. We have a failure analysis system that we use. Cobalt, which is the scheduler for the big machine. Cluster bank, which we're rewriting right now. I created this machine time overlay graph because you can't figure out what's going on in the machine of this size. It's 49,152 nodes, which is 768,000 cores. And how do you show what's running where? And then there's event timeline. Event timeline is I take a bunch of different databases, log files, and all different things, and I'm able to create one big event for each. Like if a node fails, I can say this RAS event, this availability event, and these jobs are all associated with this one thing, and I can actually tag it. So I created a system to do that. And then from that, I'm actually training a data set so that I can automatically do it, which the version I have in alpha right now is actually better than I am. We have a data warehouse. A lot of the ETLs we run are all in, or a lot of them are in Python right now, and some we're moving back to Python. I also do some validation in Python. What I mean by validation is, like in our data warehouse, you will be able to calculate a number of this many core hours is the total machine core hours. Well, that number better be equal to the subtotals of ALCC, discretionary, and insight added together, all the way down to the project level, all the way down to the user level. So I have multiple paths to calculate the same data for different metrics. So the test harness. This is what I was hired on at ALCF to do. Basically, they said, you have 3 months. I need you to test the machine, or build a framework to test this machine. Here's these 15 apps, and we need to get this working. Basically, I used Django. I painfully connected to the DB2 database and got it connected, and I was able to come up with a website that what it does, it stores the state of each test. And this way, I needed to make it fault tolerant, so if the machine were to fall over or disappear, that the state would still be maintained. I also built the client side, which connects to this database, and it is the actual runner of the tests. And I was able to build this in 3 months, and then for the next like 12 months, I was adding features to it, making everything simpler. The actual test harness, what it does is it'll actually check out a test from SVN, which could be hundreds and hundreds of megabytes. Then it will build it, so it'll actually take and build it. This could be a massive application like Milk or GPAW or NAMD or something like that. And then it will ensure that it works at that stage. It'll progress it to the next stage where it actually submits it to the scheduler. And then it will confirm that the results that it produces are correct. This sounds somewhat easy, but the problem is not a lot of scientists like making their code automatable. The build process is not simple. So we had to go through and painfully go through and get all of these apps up to that level. And then on the other side, once the job has been completed, well, it exits, but some of these aren't like true or false. It ran or succeeded. Some of them are they're converging, or is it converging, or is this number way in this deep file somewhere, 1 or 2 or something like that? So we had to identify all that and actually automate all of that. Some of the things I have found, I was able to find with the test harness were a lot of file system issues, which were fixed before all these were fixed before we accepted the machine, but identified failed nodes. I could make power supply sing. That was kind of neat. A lot of people didn't believe that, but and basically pushed the machine to the limits. So here's parts of the test harness. There, over there is my web page in Django right there. That shows each of the tests and the status of what they are. They're paused, or if the last time they ran was successful. And then over here is that's just a few of the libraries I used. And then here's the actual client running. So you can see that you'll have all the messages going out here. This also went into a database, so I had all of the messages from every time it tried to change the state of a test. So here's just the output of a test. And what it shows is that the green is the test succeeding, and the red is failure. As you can see, that we had another requirement for acceptance that the variance in the runtime had to be very small. We actually set a level. And this one, as you can see, on our blue jeans, the test runtime is, the runtime of apps is very constant. A lot of other machines that have shared I/O and stuff, they'll actually deviate quite a bit. Those 2 dots are boot failures. Then here's a single test. This test was just probably a simple matrix multiply or something. But basically what I do is I blast the machine with these tests and basically over and over and see how they vary. As you can see, there's a lot of red dots. Those are the boot failures I was talking about. And if you look right next to the line, it says like 2048, 4096. That's the size, the number of nodes. So multiply that by 16. That's how many cores it was using. All right, and then I wrote a tech article about my experience writing a test harness and actually testing the machine that you can get from here. You can Google automated testing of supercomputers. So another thing we do with our machine is we check all the jobs that have an exit code of non-zero. The old system was built very quickly, and there's a lot of crosstalk. So there'd be what we call a master, and their job is to take. We have a program that runs. It generates all the failures, and then it gives some information about them. One person would actually take all the data from all of the people in the room and try to jam it into one document that would resend back out. And then we put it in a database. Problem is, there's a lot of crosstalk, and it ended up being complicated. So I worked with one of my students, and I had him build a real-time interface, a web interface using JavaScript and stuff that had drag and drop. So I was able to get that data instead of from an email into a web interface that in Django that you could actually see the failures and you could move them. And on move, it would actually update the database in the back end. It sped up the process a lot. The meetings became almost silent, which was really weird. And I tried to bring as much data to one place because they were scraping log files and stuff. So I watched them to figure out what they're doing, and then I'd go after those log files and bring them up into the system so that they could actually see it. Here's the actual interface here. It's drag and drop. You can actually see this one right here is actually, I was actually moving it at the time. Basically, the top one is they're grouped by temporally. So if there's a bunch of jobs that fail near each other, they'll group together. So like this one was 3 of them together. But then you can move them around or separate them, especially if one is actually user error and one's a system error. Top one is one of the people in the meeting did was they annotated with the actual problem. So we actually found the problem and we classified it as user error. The second one was flagged by our system as system error, but we went in and dug deeper and found out that the job actually did succeed and produce valid output. And then the red one is a link error. That means the lines between 2 nodes were actually failing, and the job was killed because of it. And the rest down here were just user errors with some explanation on why. So Cobalt is the scheduler for the machine. Basically plays Tetris with the machine. That's what this thing does. And it tries to maximize. Well, it tries a number of things. We run big jobs. If our goal is to run jobs that run over 8,192 nodes or more, that means, that times 16, that's how big the number of cores we want you to run on. So it maximizes that, and it efficiently backfills in the time so that basically you might be able to run this little job, but run time's too long, and it's going to block a bigger job. So it'll choose the priority over that. This is an open source project that's being developed, and we run on all of our machines. It outputs data in the PBS format to be consistent with some of the other schedulers. We also have a database on the back end of this. It works with clusters, works with blue jeans. The cluster one is about to get a massive upgrade because, well, our next machine is going to look more like a cluster because the blue gene line is no longer being built anymore. It ties in, the current scheduler ties directly into the blue jeans control system. So it is also in charge of actually booting the nodes and actually telling it to stop and start jobs. We have different interfaces for different type of machines, which we're trying to clean it up so that we have the smallest possible piece of code that makes the machines look abstract enough so that they all look the same. There's also a job simulator that you can help to test and see what different job loads look like. And as I said before, it's actively developed. Cluster Bank is the new accounting system. that we're building. We had an old version. It had a number of problems. A lot of the business logic was like it was embedded in the code, and the problem with that is you'd get these weird problems, and they were embedded, which caused problems that we had to later fix at ETL time and in the warehouse, which was not very useful. So basically, it answers the questions of how many core hours were run, where did they run, and who ran them. And basically, the new system, the business logic will be isolated, and it will also have real-time interfaces. So one of the problems is it's a daily charge to jobs. Well, if someone sees their allocation is going to run out tomorrow of time, they'll submit a massive amount of jobs, and the machine will accept them because they haven't run out of time yet. Well, the new system, it'll put a hold on their account, and it'll actually be more like a actual bank. And we're using a data abstraction layer. Right now, we're using SQL Alchemy, but we're using it in a way that we will be able to switch to either Django or even Web to Pi. And very customizable. We want it so that the pieces, the known pieces like the business logic, are very isolated, so we can have versions of them and we can upgrade it very easily. Another thing I built was as I said, the machine time overlay. This is what a job looks like on our machine. It is queued at this point. It is actually started at this point. It ended here, but this is where they predicted it to end. This is the location it was run on. It's blue because it succeeded. It was a return code of 0. And here's a better one. So this is a graph of how tightly packed the machine is. Basically what it shows is if you were to look from the top all the way to the bottom, those are the mid-plane. We have, on our machine, we have something called a mid-plane. So instead of allocating each single node, we allocate in groups of 512. Well, in 49,152 nodes, there are 96 of them. So there are 96 possible blocks from 0 to 95 there. And what it is each one of these is a job. You can actually zoom in and see what job ID it is, and I actually have an SVG version of this that you can display on a web page that you can actually click on these jobs, and you actually can go find more information of them. This is useful because it actually can show you how the machine's packing without, I would not know how you'd have to find some weird way of figuring that out in some other way, but so I created this visualization to do that. You can see reservations. There's a reservation. It shows down there, but it's way up there. There's also another reservation here. Those are probably when the hardware was down. They reserved that spot so nothing could be scheduled there. And you can actually see when you run a job on our machine, you can run a script job that will run a number of small MPI tasks. You can see all the little tasks. This is that little box. See how there's an orange border? That orange border means that the job actually was non-zero, but the task was killed because it's green. And then here's someone running a bunch of little 512 node jobs inside of a larger job. Oh, this is the workday. So right there is the workday, the blue box. So that's 7 days right there. And as you can tell, some of these jobs they're very long, 12 hours. We have 24-hour jobs running at 8K or bigger, some full machine jobs like that too. This is another one. This is a single day. And it just shows some more jobs. Then I said, well, so when I made the library, I try to make things modular. So I said, why can't I apply this to our coolant data? So I just said, okay, I extracted the data from the coolant system, which was very large, so I did not put it in a database. I actually stored it in HDF5 files. It's like 20 gig right now. But what it is coolant is captured via rack, not by midplane. So each of these blocks is 1,024 nodes. And this is the coolant output temperature from it. What's neat here is I can tell where the jobs are. That graph right there relates to this graph. You can actually see where the jobs were running. And those real bright white ones over there, so the hotter the temperature, or the whiter the temperature, the more power or higher the temperature. and the cooler, the darker. So those jobs over there, they're lattice QCD jobs. They run very hot. This is the power, the same graph, but with power. So you can actually see there's somewhat of a shift in it. And I wish I had more time to actually go into diving into this and maybe doing some failure analysis, because I know we annotate the nodes that fail, but we could use the power, we could use the coolant, we can use all kinds of other things to figure out what's going on these machines. There's voltage, it's voltage. It goes up and down about 5 volts a day. I don't know how useful this would be, except for that you start seeing bands in it, like this. So maybe the copper connection's better on that one than another one. That's the other thing with coolant. We can actually go, there's another temperature one. We can actually go down to the node level. I actually did some analysis on a single node card, which contains 32 nodes, and it actually shows, it should show that the temperature rises as the coolant flows through the line, but it's not doing that. So that must mean that some of the heat sinks are not perfectly clamped to the actual nodes. And then event timeline, this is the system I built to annotate the events that happen. We have various things that this will show. It shows, well, it'll show what happened to the nodes down to a node level. It can show problems with node cards and coolant sensors and all kinds of things. One thing we really look for is RAS. RAS, those are events that happen at a given time that really tell us what happened on the machine. Here's the actual. This uses a Django site on the back end, and what it does is it's using timeline.js. It'll actually pull the data out and it'll actually format it like this. And there's an interface that you can actually click on these things and see where they're actually coming from. So this is a period of a few hours, and you can see there's a RAS event right here that happened. Most likely it says like a memory module destroyed or something. And then you'll see the machine automatically marked it unavailable. And then that's where someone service actioned it to come back up. And then here's the Cobalt scheduler actually putting a reservation on it. And here's me putting my annotation that joins all of those events together. And that's an event that was generated from the failure analysis meeting. Basically, this brings a bunch of the data sources together. And then there's the example of the RAS event. A2 machine processor check. That means it's a bad node. We write a lot of the ETLs in Python, and we have a lot of them. The nice thing about this is that one of the first things I did after I was done writing the harness was I went around and found all the business logic, put it in one library, heavily unit tested. I think it's over 80% covered right now. That way that people know we can actually, if our manager wants to know what is the current way we calculate availability, there's a single function, there it is. And they said, well, what if we put these numbers in? We can actually make a test that'll actually put those numbers in and test to make sure it comes out to what they want. We are trying to make these ETLs as readable as possible because we have a lot of them. Separate the business logic, as I said. And I try to use a lot of the libraries from the community, such as NumPy, SciPy, Pandas. I've been playing with a lot to assist on doing this. Pandas has been really helpful on doing this. These are just some of our ETLs. Basically, we have a lot of test ones and prod ones, and basically we'll be able to, we have to be able to test these things before we release them. So these are just a few of the systems we run. So there's the ETLs from the cluster bank system over to our warehouse. Here's some of them to our old warehouse, and to the new warehouse. We maintain those so that we can actually validate the data. There's another ETL that takes it to a raw table so that we can validate a different way and actually get a different set of data. These are the ones that extract part of the control system, which contains all the environmentals. That's where we have the billions and billions of rows. And then there's where it dumps some of it to HDF5 files, because our database would not would not work very well with that. Here's some of our validators. They check for specific problems. If we've ever encountered a problem, like an errant charge or something like that, we will actually make a single query that will find those. We will assert that it finds them, and then I will fix it, and then the validator should just stop complaining. So we have a lot of these, and they find very weird things at weird times. We have large sets of data. I've been talking about environmentals a lot. I'm not going to call it big data, but we have a lot of it. And the file system. So one of the projects I actually did in my CSC 503 class with Massimo was I took the file system data that we had, and we had a piece of code that would parse this code. I isolated down to one piece of code that took about an hour. And I said, what if I parallelize this? And what I did is I took it and I used MPI4Pi. I was able to parallelize it and run on our Blue Gene machines. So I'm actually running Python code with NumPy and Pandas on our Blue Genes. The minimum number of nodes I could use was 128, and I'll explain why. But, well, memory is one constraint. I did not optimize it for memory, so we had another node which I ran it on. It took 417 gigabytes of RAM to run, because you could probably tell it was stored in memory 3 times. Once I hit a problem in MPI4Pi that what happened is when you'd use 64 nodes, the offsets into the files were bigger than an int32, and MPI's default size for a lot of their functions is an int32. So I was hitting it, and it was turning into some really small number, and I was like, so I actually went over to the MPitch team, which is down the hall, and I was talking to them about it, and they confirmed that, yeah, it's an int32 problem. And then I was thinking, when you're in Python, you're not worried about these type problems. So I actually contacted the MPI4Pi guy, and we worked it out, and I said, it's not really a bug, but like you should probably get a warning when you're casting something and it's overflowing. And he agreed, and so the new version of MPI4Pi actually will warn you on overflows. If anyone knows NumPy or C-types, they have the same problem, but they do not warn you. So I did a sort of a study. I ran it at different sizes, and here's the graph that actually shows the different runtime in seconds. Basically, it's greater than 100 gigabytes of data. It counted 236 million files, and this was in 2013. It's an old data set. There's about 8 petabytes in there. So serial took about an hour, and parallel took less than 2 minutes. And you can see that right around, so this is the log size of the nodes because the graph gets way spread out. But right around 32 nodes, or 16 and 32 nodes, it deviates because you're now running in hardware threads. And you start losing performance for various reasons that I need to look more into. Yes, we have a lot of nodes on our machine. And each one has a temperature sensor. This is what I was talking about, a lot of data. So it's 4.7 million rows per day. And we have a bunch of other environmental tables like this. Basically, what's next, I'm going to be trying to move stuff to more real time. A lot of abstraction. I might do some of the more parallel stuff, especially with some of the longer running ETLs so that we can push them to near real time. And basically try to do some more analysis on the actual data. And then I could try to write the presentation in Python, but that might be difficult. So, questions? Yes?
So I have 2 questions.
Sure.
The first question is, looking at RAS, R-A-S, my question is, what is the most important out of those 3?
Oh, what is RAS?
It is, but out of those 3, are they all equally important, or do you say one is
Oh, you know what? I forgot what the 3 are of RAS, because we deal with RAS events. But so what is most important about RAS, or reliability, availability, and serviceability? For us, I think it's reliability, because with 49,152 nodes, we have it seems to be around 2 to 3 nodes fail per week. And as you increase the number of nodes, you just end up blocking bigger jobs. And our goal is to run bigger jobs. And we need to keep those nodes up, which also leads to availability and making sure the machine's available to run.
We're out of time, but thank you. I'm sure you'll be I guess it's working now. Thank you. I'm sure he's willing to answer questions during our coffee break. We'll come back here in an hour. Thank you.